Right. Okay. In the last class, we started the long-term behavior of the difference equation, right? Right. So we know that we completed this 4 or 5 slides in the beginning of the chapter. However, I will recall what we did. So in generally, in the dynamical system, it is very important to understand the solution with respect to the long-term behavior. So what is that meaning of the long-term behavior? So that is the behavior of the solution A of n as n tends to infinity. So simply we are going to analyze the solution limit n tends to infinity A of n, right? So this one, what I am mentioning here, limit approach for the useful for the analytical solution of the problem, if you know that one, right? So there is no guarantee to get the analytical solution for all problems. So in such a case, we need to analyze such a behavior with respect to other methods, right? We will see what type of methods we are going to discuss in future, right? So in this chapter, we are going to discuss the long-term behavior of the dynamical system and relevant graphical methods, right? So, for example, we are going to the features of the first order difference equation in the form of x of n plus 1 is equals to f of x1, right? So we know that the behavior of the solution of this model as n tends to infinity. So that's why what we uh, discussed in the earlier slide, as n tends to infinity, we call it a long-term behavior of the method. See, for example, in our material, in the first example, let us say the dynamical system A of n plus 1 is equals to k times A of n, where A of 0 is equals to A naught. So this is our initial condition. So we know that the solution of this simple equation is A of n is equals to k to the power of n times A naught. So A naught is a fixed amount. So now what we are going to discuss the long-term behavior of this solution. That is, as n tends to infinity A of n, A naught as a constant, limit n tends to infinity A of n. That is A naught times, there are different possibilities of the k. So if the k value, either positive or negative, which are lies in between 0 and 1, which is equals to less than or equals to 0, and it is strictly less than 1, then the behavior is 0, right? We know that, for example, if you take k is equals to 1 by 2, and k to the power of n is 1 by 2 to the power of n, that tends to 0 as n tends to infinity. So if the modulus of the k value lies in between this range, the long-term behavior is approaching to 0. So what will happen if k is equals to 1? Then we know that obviously it is a 1. If k is equals to -1, this will be oscillating because -1 to the power of n. So the values are lies in between -1 and +1. If it is before a naught, the values are lies in between minus a naught and plus a naught. So what happened if the values of k, the range is greater than 1? So then the behavior is unbounded. So this is the behavior of the long-term behavior of the solution. So we know that the application, what we discussed in the earlier, either in chapter 1, in the beginning of the middle of the chapter 1, right? So there are a lot of application for this one. If you consider that model, that is a of n plus 1 is equals to k times a of n, then the solution is a of n is equals to k to the power of n times a naught. So this is the solution. If you apply this one is under the radioactive decay. So if we know that the values of k lies in between 0 and 1, the radioactive stuff is slowly disappearing over the time, right? So similarly, this same idea, same model, we can also apply the population model. So if the k values lies in between 0 and 1, so we can see there is a decline towards the 0, and k is greater than 1. We know that what we see the previous slide, this approaches infinity. So that is unrealistic endless growth. So this is not possible. So because a lot of real world factors like limited resources can change the growth of pattern. So for instance, you can see the bacteria in a dish initially multiply quickly but slow down as resources run out. So if you want to test the bacteria in the dish in the sense of the biology, what happened in the beginning, the process, the population growth, the bacteria growth, the cell division, it is very quick because in the beginning there is a lot of resource. But after that, the population growth is going to slow down because the resources are run out, right? So what is this model? This model is okay for the short-term predictions, but it is too simple for long-term guesses, right? Because that is not possible because this value is tends to infinity as n tends to infinity if k value is greater than 1. So now we will see all these with respect to the graphical point of view. Suppose if see here, the k is equals to 0 and your initial is 1000, then this value is approaches to 0 as n tends to infinity. So that is the values are, see here, the graph is gradually 0 as n tends to infinity. And what about the k value? So in the beginning, we discussed the values lies in between 0 and 1. Then the a of n is equals to k to the power of n. This value is tends to 0 as in n tends to infinity. If you take the k value is 0.9, which is a less than 1, and a naught is 1000, see in the beginning, there is a decay as uh, uh, over the time. So for example, if you see on the graph, after the 40, the values are approaches to 0. So you can expect the population decay or bacterial growth So the n is equals to either 30 seconds or 40 seconds. They are the growth is or radioactivity, the growth is decay and gradually it is vanish, right? And similarly, if k is equals to 1, see there is no, it seems to the parallel to the x-axis. That is, this is an a of n and this is a n and this is a of n values. So over the time, there is a constant which is parallel to the axis. That is a constant with respect to the initial condition. If k is equals to -1, then a of n is equals to -1 to the power of n to n times a naught. So as n tends to infinity, the values, because the oscillation between -1000 and +1000, because your initial value is 1000. It is oscillating mode, right? And similarly, if you take the mod k is greater than 1, right? Suppose if you take -0.9, which is a greater than -1, and a naught is equals to 1000, and here is k is equals to -1.1, and the mod k is greater than 1, then the values are in the beginning, in the negative value is oscillating a periodic, and then it is gradually vanish. And here also beginning is the vanish, and then the periodic status is starting from after 50 onwards, where n is equals to 50 onwards. So this is one of the way to interpret the long-term behavior of the solution. Right? See here, this is a k is equals to 1.1, that is a greater than 1. So it is gradually increasing as n tends to infinity. So that is the homogeneous form of the first order difference equation. So what about the non-homogeneous difference equation? If it is plus c, k times a of n plus c and initial condition a naught, we know that we proved the solution of this one is k to the power of n times a naught plus c times, this is k to the power of n minus 1 over k minus 1, where k is not equals to 1, and n when k is equals to 1. So we proved this is non-homogeneous. We know that the solution is complementary. A of n is equals to complementary solution plus particular solution. So this is our complementary solution and this is our particular solution. So now we will see the cases. What about the behavior as n tends to infinity, right? So here is n, here is n, and here is n. So based on different values of k and the combination of the c, there are different possibilities we will see, but not all cases we are going to consider. We are considered some cases here. So if k is equals to 1 and your solution is a of n is equals to a naught plus cn. So what is the long-term behavior as n tends to infinity, a of n? The right-hand side is infinity when c is greater than 0. And a naught when c is equals to 0. It is minus infinity when c is less than 0. So here, that is the long-term behavior of the solution. So what about in the case of k is equals to 0? So k is equals to 0, then you will get only uh, Cn, a of n is equals to, if you see the equation here, as n tends to infinity, this will goes to 1, right? And you will get only the value is the c when k is not equals to, or k is not equals to 1. So that is your A of n is equals to C. That is C tends to C as n tends to infinity because of the constant. So similarly, if the k value lies in between 0 and 1, and your A of n is approaches to C over 1 minus k as n tends to infinity. And if k is equals to 1, this is an equation A of n, then that is alternate to between the A naught and C minus A naught as n tends to infinity because of the nature of minus 1 to the power of n, right? And if if mod k is greater than 1, then the long-term behavior is equals to minus infinity under this condition, right? Because this is the right-hand side value of the solution. And infinity if this value is greater than 0. And is equals to 0, that value is equals to C over 1 minus k. See here, there is a finite values, some cases are the unbounded, right? So we can estimate based on the problem, we can interpret the real world. So under what circumstances we are going to get the finite values as n tends to infinity, right? And under what circumstances our long-term behavior is unbounded, either minus infinity or plus infinity. So this is best example under the Fibonacci sequence, that is a rabbit model. So we know that this is a second order linear difference equation. So that's why we need a two initial conditions. One is f of 0 is 1 and f of 1 is equals to 2. Then already we proved that analytical solution of this Fibonacci sequence for the rabbit model, this is. So we know that the value 1 plus root 5 over 2, we call it a golden ratio, right? When this value is greater than 1, then the long-term behavior is approaches to infinity as n tends to infinity. But you know that what is the real world factors? There are a lot of factors uh, involving to maintain the finite value. That is the different scenario. We will see. So what is our major interest? The major interest is the solution A of n of a discrete dynamical system remaining close or approach a finite value as n tends to infinity, as n increases, right? So what is that meaning? What is the sense of the close? What is the meaning of the approach? So mathematically, we are consider closeness mean the distance. What type of distance? In one dimensional, we can take the modulus. And if it is a two-dimensional, the distance between 2 points, we can take the Euclidean distance, etc. So what happened? Because of this information, we are going to identify an important concepts, so-called equilibrium point and the relevant notion of the stability, right? Okay. So we need to discuss what is the equilibrium point. So before going to the equilibrium point, we need to define what is the fixed point, or sometimes we are calling the invariant point, right? Suppose you have a function f of x, right? Under what circumstances this function value is invariant? What type of points on the domain? Such a point we are calling the fixed point. See the definition, formal way. Suppose a point A star in the domain of the single variable function f is called a fixed point, and also known as the invariant point of the function f if the condition is f of a star is equals to a star. So that is, what about the action on the point a star? F is a action on the point a star, then the output is also a star. Such a point we call the fixed point. See, for example, the f of x is equals to x square, where x belongs to R, then any fixed point a star of f satisfies f of a star is equals to a star. So in place of x square, you can substitute in place of x, that is a star whole square minus a star, that is a times a star times a minus 1 is equals to 0. And that is the product is equals to 0 mean that a star is equals to 0 or a star minus 1 is equals to 0. So a star minus 1 is equals to 0 implies a star is equals to 1. So then you can say that f has two fixed points. So in graphically, you can see this is your x-axis and y is equals to f of x. We know that this is the line passing through the origin, that is equals to y is equals to x. And you know that f of x is equals to x square. Then I can draw roughly this is. So you can expect what are the fixed points where this graph is touching the line y is equals to x. So here, this graph y is equals to f of x touches at the origin 0 as well as the point 1. So there is a link between the fixed points, identifying the fixed point on y is equals to f of x, and where that function is, that curve is intersect the line y is equals to x. Suppose if you take the f of x is equals to x, that is, this is. So the line y is equals to x and f of x is the coincide. So every point on the x-axis is a fixed point, right? And also you can take the f of x is equals to x square plus x minus 1 where x is greater than 0. When we substitute those values, you will get the a values. One is minus 1 and one is, sorry, plus 1 and minus 1. But here you have to see, basically this function has a 2. But under this condition, x is greater than 0, we have to neglect the minus 1 because minus 1 is less than 0. But your points are should be a greater than 0 because of this condition. So that's why there is only one fixed point, that is 1. Right? So here in the first one, there are 2. In the second one, the infinite number of fixed points, and the third one, only one fixed point. Can you expect, is any function have means no fixed points? Yes, there is some functions are there. You can see the example, right? That is f of x is equals to x plus 1. You can see which point is f of a star is equals to a star. Can you find any such a point on the real line? Is it possible to find a point a star such that f of a star is equals to a star for this function? Right? Impossible. You can't find such a point, right? So there is no fixed points. What is the conclusion? The fixed points may or may not be exist. If it is exist, those fixed points either more than one or infinite number of fixed points or only one fixed point. So then we can see there is an example with respect to your calculus based course. So in graphical terms, what I explained in before, a fixed point x means the point x comma f of x is on the line y is equals to x. Or the graph of f has a point in common with the line y is equals to x. If you see this is a function, this is your f of x that is equals to u to the power of minus x minus sin x. So this function is intersect with the line y is equals to x at the point that is x is equals to 0.354463. Of course, you can't find any exact natural number, but there is a real number is a positive. Similarly here. So this is my function cos x plus x square over 2x cube plus 5x. And this is a graph y is equals to f of x. And this graph is intersect only at the one point, right? So that is 0.814787. This is called a fixed point, right? So for your standard, this is the requirement. If you are going advanced level, one of our students are identify the such a functions in different aspects and he got the patent, right? So the fixed point is not only a single, it is a vast information in advanced level. Okay. So now, based on that fixed point, we are going to define what is the equilibrium or fixed point, right? In our dynamical system. Suppose a point A star is called an equilibrium or fixed point. Sometimes they are calling a stationary point, right? There are different names, right? So that point is said to be a equilibrium if that point is a fixed point of the function f, right? That is, we have to show that f of a star is equals to s, right? So for such a property for the dynamical system, such a fixed point, we are calling the equilibrium points, right? So what is the importance of this equilibrium? Sometimes it is useful to analyze the behavior of the solution, not only the AN, near to its solution, near to its equilibrium point, right? So if they exist, we are going to discuss the behavior of the solution for that equilibrium points, right? So what is in particular, we wish to determine whether or not A of n remains close to an equilibrium point as n tends to infinity when the initial value A of 0 is near that equilibrium point, right? Because we don't know A of n is a lot of terms, but we know the initial point A of 0. Then we need to find the relation between the A of 0 and equilibrium point, right? So as n tends to infinity, what is the closeness in between these 2 points? So now we are going to define based on this closeness. What is the close? We are going to define the different terminology, right? Suppose this is our equilibrium point, A star. And for the discrete dynamical system, A of n plus 1 is equals to f of an. And with the initial condition, A of 0 is equals to A naught. I am going to say this one is A star. The equilibrium point is said to be stable if for any epsilon greater than 0, there exists a delta greater than 0. So this is delta epsilon notation for the stability. The initial condition and equilibrium, the distance between these 2 points is less than delta, then it will be same. Of course, the delta is depending upon the epsilon, that A of n minus A star is less than epsilon for all n greater than 0, right? So whatever the distance is between less than delta, as n greater than 0, as n whatever the n value for the large value, the distance between the A of n and that equilibrium point distance is again a small, less than epsilon. So in such a condition, we are going to say that the equilibrium point is stable point. Otherwise, what happens sometimes? The distance is less than delta, the initial condition and A naught. Both the distance between those two points is less than delta. But what happened as n increases to as n greater than 0 or as n increases, this distance A of n minus A star is greater than or equals to epsilon. Such a condition, we call it unstable. So simply what we discussed in the previous example, as as n tends to infinity, whatever the output is infinity, we can say that one is unstable. So this one, in the words, if A star is a stable, if whenever the initial value A of 0 is sufficiently close to A star, that is a distance less than delta, each of the remaining values A of n where n greater than 0 of the solution remain close to A star, that is distance less than epsilon. So that is called the stable, right? So now there is another definition, the attractor. Suppose my equilibrium point A star is said to be an attractor if there exists a neta greater than 0, such that, see the distance here. The distance between the equilibrium point and initial value is less than delta, implies as n tends to infinity, you will get the equilibrium point. Such a condition, we are calling that equilibrium point as an attractor. If here the neta, what is the meaning of this one? The A star, this is an A star. The A star is lies in between A naught minus neta and A naught plus neta. So there is an interval in between. In this interval, there is an A star. So if neta is equals to infinity, that is, what is that meaning? That is, this is a less than infinity mean any value. There is no exist, not an exist. For any value, the distance is less than finite, then the value is equals to A star, we calling as a global attractor. So attractor and global attractor is depending on the existence of the neta. This is true for every positive, then we call it a global attractor. So you may thinking n is equals to neta, n is equals to neta is equals to infinity mean this length is infinite length. No, that is when it is modulus value is less than infinity mean this value should be a finite. So that is any value in place of neta, you can take any value of neta, not a particular value, you can take any value of neta, then as n tends to infinity, it will be A star. Such a condition, we call it a global attractor, right? So what is that interpretation? That interpretation is A star is an attractor if whenever the initial value A of 0 is sufficiently close to A star, that is the distance less than eta, the solution A of n converges or is pulled towards A star, we call it is a attractor, right? So in particular, A star is a global attractor if the solution A of n converges to A star for any given initial value A of 0, right? Any question for the concept of the stable, unstable, attractor, global attractor? So there is one more definition.
So before you move on, you could go over the attractor, please, thanks.
Sorry?
So before you move on, you could go over the attractor, please, thanks.
Yeah, that is, you will get the finite value. That finite value is equals to equilibrium point. Is it clear? Hello?
So we can continue.
Okay. So there is another one more definition. We are going to say what is the meaning of the asymptotic stable. So the equilibrium point, I am going to say asymptotic stable if it is a stable plus an attractor. So stable plus attractor, we call it asymptotic stable. Suppose if the in place of attractor is a global attractor, right? Stable plus global attractor, we call it globally asymptotic stable. That is, the A star is a global attractor if the solution A of n converges to A star for any given initial value A of 0. So there is no restriction of the initial value. Any initial value, it will be approaches to, the solution is approaches to A star as n tends to infinity. Right? So what is the remark? So see, this is the determining the stability of dynamical system using the above definition is very difficult in almost all cases, even if you know the analytical solution is known, right? And furthermore, it is impossible if the analytical solution cannot be formed. So the determining of the stability nature is generally difficult for the analytical solution is known. But whereas some cases we can't find the analytical solution. For example, there are some class of nonlinear difference equations. We need to only identify the numerical solution. So in such a case, the finding the stability nature, such a problems, it is very difficult, or in other sense, we can say it is impossible, right? So whatever the cases, we are going to require more feasible ways of investigation of the stability in the dynamical system. But there is one simple theorem is there. So we can use that theorem for the discussion of the stability. What is the theorem? So this is my difference equation, and A star is an equilibrium point of the difference equation. So once if you know the difference equation, that is we know that what is the f of x, and you have to find f dash of x, and then replace x by A star, that A star is an equilibrium point, and take the modulus, right? What is this modulus value? The derivative of f at A star is strictly less than 1. We can say your A star is asymptotically stable. So what is that meaning, asymptotically stable? That is, two parts are there, stable plus attractor. Suppose the first derivative at A star is greater than 1, you can decide that A star is unstable. But what is the case? When the first derivative at the A star is equals to 1. So we can't make any conclusion for this condition. Right? So in order to determine the stability of the equilibrium point, in this case, what we are going to do, some graphical tool, which is known as Verhoeven's diagram, or sometimes we call it a stair step, because when you draw the diagram, it looks like a stair steps. Or some authors, they are calling the cobweb diagram. Right? What is this one? So just as usual, for example, this is the plot, and first we need to draw the line y is equals to x. Right? And then you can see suppose your suppose your graph y is equals to f of x. This is y is equals to f of x, and this is the line y is equals to x. Suppose this is a point. This is an A naught. So this is the axis is A of n axis, and this is A of n plus 1 axis. Suppose this is your A naught, right? Isn't it? So your equilibrium point is like here. This is an equilibrium point, right? What we are going to do, first we need to stair step plot mean the diagrams are horizontal lines and vertical lines, right? So you need to draw the diagram, right? And write of course, write the parallel where it is a touch, that is an A1, and you can draw the another vertical line and draw the horizontal, again vertical line, and draw the uh, vertical line, and again the horizontal line, right? What happened? This approach towards to A star, then we can say that one is a stable. If it is far from A star, we can say that one is unstable point, right? See, for example, there is a uh, steps. First, we need to draw the plot horizontally from the point A of 0, comma A of n to A of 1, comma A of 1. So that is an horizontal line. After getting the A1 and you have to draw the vertical line from the point A of 1, A of 1 to A of 1 comma A of 2. So you have to continue iteratively. This is the a general, because here A of 0, if you put k is equals to A of k minus 1 comma A of k, if you put k is equals to 1, you will get the first point, right? And the second one you will get when you substitute k is equals to 1 in this one. So this is the general one. So constructing the horizontal lines and vertical lines of the graph between the y is equals to f of x and y is equals to x, and repeated those steps a comma b, right? You will get a steps plot, right? So what happened? An asymptotically stable equilibrium point is characterized by a stair-step plot that moves from the initial value A of 0 towards the equilibrium value A star, right? So that is the A naught, whatever the staircases, right? So this is a star and A of 0. That one is towards to the equilibrium point. The A of 0 is moving towards the equilibrium point. We call it a asymptotic stable equilibrium point, right? On the AN axis. Whereas the unstable equilibrium point is characterized by a stair-step plot that moves from A of 0 away from the equilibrium point. For example, here is equilibrium point. Your stair steps plots is away from the equilibrium point. That is, a steps is moving from here. Suppose if I draw this one, this is y is equals to x, and if you put this one, this is your a naught. It will going to above, away from the your equilibrium point. So in such a case, we call it is a unstable, right? But there are two other options. What is that options? Sometimes there is no movement. It seems to be flat. That is called a stable. Sometimes it is only finite number of periodics. In such a case, we are going to consider as a stable point, right? So we will see for all this one with example. See, we know that what we discussed in earlier. So for this one, what is the equilibrium point? A of n plus 1 is equals to k of an plus 1. So recall this an plus 1 is equals to f of an, and you can consider this one as f of x is equals to kx, right? What is the derivative? F dash of x is equals to k, right? So what happened? F dash of A star, if you consider A star as a equilibrium point, that will again a mod k, right? But we know that this mod k is less than 1. Already we discussed in the first example that equilibrium point is asymptotically stable, right? And when k is greater than 1, there is unstable. But how do you get this one? F of x is equals to x. Only that 0 point will be satisfying this one. F of x is equals to kx. K is a constant, right? This is only possible when x is equals to 0. So that is our equilibrium point, right? So we can investigate the behavior of this system using the following state steps plots or Hog web. So here see, This first diagram, what is the your initial point is A naught is equal, initial condition A is equals to 0.1. So this is your the initial condition 0.1. So now, and K is equals to 0.9. 0.9 is less than 1. According to the theory, we know that this is a asymptotically stable. So what is with respect to the state step plots? See here, this is the line, the red line is equals to y is equals to x line. The blue line is equals to y is equals to f of x line. That is your function difference equation line. So this is a starting A naught and moving horizontal line, again the vertical line, horizontal, vertical, horizontal, vertical, it moving. What happened? It reaches to, what is your A naught? A star. A star is equals to 0. What happened? This state steps is down towards the your equilibrium point. So in such a case, we can conclude that solution is asymptotically stable. So here, what about the K is equals to minus 0.9? Of course, mod K is less than 1. What happened? If the starting, this is your A of 0 value, this is the starting, because of the K value is negative, see the moving. This is horizontal, vertical, horizontal, vertical, horizontal, vertical, and moving towards where it is going, towards the 0. 0 is your equilibrium point. See the state step plots and what is the theory, we know the analytical solution. So both are coincide this stuff, right? And similarly, we can see the other values. Here see, K is equals to 1.0.2. This is your 0, right? This is your initial value. What happened? The state steps is going away to the equilibrium point. The steps are moving away from the your A star. So this is unstable. Similarly, here is also, it is going to away from the 0, that is the unstable. And here see, when K is equals to 1 and A naught is equals to 0, 1, both are coincide. So we can conclude that one is a stable. See here, when K is equals to minus 1 and A naught is equals to, there is one cycle, periodic cycle 1. So we can conclude that one as a stable. Right? So that is the case of the homogeneous. And similarly, we can see the non-homogeneous linear system. The same thing, this is A of n plus 1 is equals to K of n plus C, and A of 0 is equals to A naught. Isn't it? So this is, you can take the f of x is equals to kx plus c. Then f of A star is equals to A star mean K star plus C is equals to A star, and A star times 1 minus K is equals to C. Then you can conclude your A star is equals to C over 1 minus K. This is your equilibrium point. So then you can conclude that if the equilibrium point is asymptotically stable when mod K is less than 1 and unstable if mod K is greater than 1. So you can see the state step plots. This is one periodic, and what is the conclusion? For that K is equals to minus 1 and C is equals to 1 and A naught is equals to this one. This is one periodic. So then you can decide what is the condition, whether it is a stable or unstable. So this is another example. We know that this is a monthly withdrawals, what we discussed in the chapter 1. This is a non-linear difference equation, and you have to write this one as f of x is equals to this one, and you have to find an equilibrium point. Suppose if A is an equilibrium point, f of A star is equals to A star, and substitute, you will get, there are two values you will get are this table. One is A star is equals to 0, and R over 100 minus K times A star is equals to 0. That is, your K star is equals to R over 100 times, and A star is equals to R over 100 times K. So this is one equilibrium point. This is another equilibrium point. So you have to discuss uh, the stability analysis for the equilibrium points of this one, right? So you know that, see here, this is the derivative of your function, right? And at the point 0, this is 1 plus R over 100, and f dash of 100, R over 100k, this is 1 minus R over 100. And here is R is there, but we don't have any condition. Now we need to verify whether it is a stable or not under the condition of R greater than 0. If R greater than 0, this value is f dash of 0 is greater than 1. So you know that equilibrium point is unstable, and R greater than 0 under this condition. But you know that R over 100, if R is greater than 1 minus positive is again positive, which is a less than 1. So this value is under the equilibrium point, this is asymptotically stable, right? So how do we get the equilibrium points? And then how to apply that theorem? The derivative of f dash of 0 is greater than 1, therefore the equilibrium point is unstable, right? Under this R over 100k, where R is greater than 0, this equilibrium point is asymptotic stable. So how do we visualize this stable point with respect to the state steps diagram or cobweb diagram, right? So let us take
It looked like Sue get kicked off, so we probably give him 5-10 minutes, and if he ain't come back, we just leave.
Hey everyone. Yes, so Dr. Rao just called me. It looked like power went by him. So he said that that'll be it for today's class, but whenever the recording finish process, he will put up the link on the My e-learning page. Okay, so that's it for tonight's class.
Hi, Vigash. Are you still here?
Yeah.
Do you go in? Do you be in the math help center? Like, do you go there?
Yeah, so I'm there Mondays from
Mm-hmm.
9 to 12.
Okay, only on Mondays.
Yeah, I was actually there today.
Really, actually, I was in the math help center and no, there was nobody there to help with 341. So
Oh, you were there in the evening?
no, I was there throughout I reached the school, like I actually came to school for the math help center, so I reached the school like around 11 o'clock, and then they told me to
Okay.
come back around 1 o'clock, and then I ended up coming back, and then I ended up coming back around 2 o'clock, and still nobody was there to help. So
Yeah, so 11, I would have just left because I was there from 9 to 11 today.
oh,
Okay, well, can you make it Monday from 9 to 12?
sure, yeah. But the thing is, I mean, I know you're kind of help with the assignments, and that's okay. I'm not trying to get like no full help with the assignments or anything, but I have a code that, and I mean, the entire assignment is bugging me, but this particular code, I think I'm doing everything that I'm supposed to be doing, but it's not running. So I really wanted help before the assignment due Friday, but I don't know if I'll be able to.
Do you have the code now? Will you be able to show me it now?
Yeah.
Okay.
To share my screen.
Yeah, go ahead.
Yeah.